Hopefully you're familiar with SOLIDWORKS' equation-driven curve function, which you can use to create many different types of curves. There are two ways to sketch a sine wave that forms a closed circle, depending on the orientation of the sine wave. Here, I have a simple cylinder part file. The cylinder has a 3-inch radius. To sketch a circular sine wave that wraps around the cylinder is easy. I'll begin by creating a new 3D sketch. Next, I'll launch the equation-driven curve tool. For the x value, I'll enter the radius, 3, times the sine of t. For the y value, I'll again enter the radius, 3, times the cosine of t. This is the simple parametric equation of a circle. Before setting the z value, I'll set the parameters so they go from 0 to 2 pi minus 1/1000th of an inch. If I have the parameters go a full circle to 2 pi, I'll get an error when I try to complete the curve. Now, for the z value, I know I'll need to have a sine function, but if I simply enter sine of t, you can see that the preview looks incorrect. That's because we need to add some scalars. Inside the sine function, I'll enter the number of oscillations I want to occur over 360 degrees. Let's do 6. And to increase the amplitude or height of the sine wave, I can enter a scalar on the outside of the sine function. Let's multiply it by 4 inches. And this creates a sine wave that varies 2 inches in both directions from the origin and oscillates 6 times before coming full circle. Now, this gets the job done, but there's still going to be a thousandth of an inch gap that I'd have to close manually using a line or spline to get a perfectly closed loop. This is due to a SOLIDWORKS limitation that prevents you from creating self-intersecting geometry. Now, what if I wanted to create the sine wave oriented axially around the circumference of the cylinder? This can get quite tricky. Although the curve would only vary in 2 dimensions, the 2D equation-driven curve feature in SOLIDWORKS only lets you specify equations explicitly, meaning for y in terms of x, or parametrically, meaning for both x and y in terms of t. But for this purpose, the easiest form is not the explicit or parametric form, but rather the polar form, which is expressed in terms of r and theta. The exact form of this equation is r equals r 0 plus either sine or cosine of theta. And again, you can use scalars to modify the trigonometric term here. Now let's say I want the wave to have an amplitude of 1 inch in both directions, and to oscillate 8 times over one 360-degree revolution. And just to switch it up, let's use a cosine wave, although the process for a sine wave would be identical. For a 3-inch radius cylinder, the equation would now look like this: r equals 4 plus the cosine of 8 theta. That's simple enough, right? But, like I just mentioned, you can't use SOLIDWORKS equation-driven curves for polar equations. To get around this, I could do some complex math to convert this to a parametric equation, but there's an easier way. What I'll show you instead is a trick to creating polar equation-driven curves in SOLIDWORKS with the help of Microsoft Excel. We'll have to use a curve through x, y, and z points, with Excel generating the points for us. Let me open a new blank workbook in Excel. I'll need 6 columns for this table: degrees, theta, r, x, y, and z. I'll begin the degrees column by entering 0 and 1, and then use Excel's functionality to populate the rest until I get down to 360 degrees. Now, I need to convert these degrees to radians. In the theta column, I'll enter the equal sign to indicate a formula here. Now, I'll enter the cell number for the first degree value, A2, times the quantity pi divided by 180. Make sure to add open and close parentheses after pi, or Excel won't recognize it. The r column is where we'll calculate our polar equation values. I'll enter equals 4 plus the cosine of 8 times b2. This value should calculate out to 5. This gives us the polar values. Now, we need to get them in terms of x and y. To do this, I can use the identities x equals r times cosine theta and y equals r times sine theta. For x, I'll enter equals c2 times cosine b2 For y, I'll enter c2 times sine b2. Finally, for the z value, I'll populate the whole column with zeros. Now this completes the table, but in order to use Excel data in a SOLIDWORKS curve through X, Y, and Z points, the data must be in a tab-delimited text file with exactly 3 columns. So I'll highlight just the X, Y, and Z column values, and press Ctrl-C to copy them to the clipboard. Next, I'll create a new Excel workbook. Now, using the Paste drop-down menu, I'll select Paste Values. If I tried to just paste regularly, the table wouldn't populate correctly due to the equations and references. Now, I can perform a Save As, and choose Text, tab delimited from the File Type drop-down. Now, let's open the text file to verify its contents. I might have to tab over the zeros like you see here. If the text file is off by even a little bit, SOLIDWORKS won't be able to load it. Now, back in SOLIDWORKS, I can go to Insert, Curve, Curve through X, Y, and Z points. I'll click the Browse button, and I'll change the files of type drop-down from curves to text files. Now, I'll look for the text file I just created and click Open. As soon as I do, you can see the values appear in the Curve dialog box, and when I click OK, the curve is created. Also, you can see the curve feature in the Feature Manager tree. Now, if I was using this for, say, a guide curve, I'd be done. But if I want to extrude this curve, there's one additional step. You can't extrude a curve, only a sketch. So first, I'll have to create a new sketch and use Convert Entities to convert the curve geometry into a sketch. Now I can extrude the profile.